Above our heads, 400 kilometers into orbit, the International Space Station circles Earth every 90 minutes. It glides in the darkness of space, shining like a bright star to those who spot it from the ground. Inside, astronauts float weightlessly, conducting science experiments, gazing back at our fragile blue planet and experiencing life without gravity. But they live in a place far more dangerous than it looks. Beyond Earth's protective atmosphere, the sun constantly lashes space with a storm of invisible radiation, a river of charged particles known as the solar wind. These particles race outward at hundreds of kilometers per second, and without protection they could damage electronics, disrupt communications, and slowly cook human DNA. So how does the ISS survive? How do satellites stay in orbit without being blasted away? The answer lies in a combination of Earth's natural defenses and human engineering, a partnership of planet and technology that allows life to thrive in orbit. The solar wind is one of the sun's most remarkable phenomena. To the naked eye, our star looks like a smooth, glowing sphere. But in reality, its outer layers are boiling with activity. The sun is made mostly of plasma, a state of matter where atoms are so hot that electrons are stripped away, leaving behind a soup of charged particles. In the corona, the sun's outer atmosphere, this plasma is so energetic that it escapes the sun's gravity and streams into space. That outflow is what we call the solar wind. It isn't constant. Sometimes it flows gently, other times it surges violently. During solar flares and coronal mass ejections, the sun can hurl billions of tons of material outward in giant clouds, traveling faster than 1,000,000 miles per hour. We only truly began to understand the solar wind in the 20th century. In 1958, American astrophysicist Eugene Parker proposed that the sun's corona could not be static. It had to expand into space. His theory was controversial, but within a few years, spacecraft measurements confirmed he was right. Today, NASA's Parker Solar Probe, named in his honor, dives closer to the sun than any mission in history, flying through the solar wind itself. But why does this matter to us on Earth? Because the solar wind doesn't just vanish into the void. It slams into every planet it encounters, shaping atmospheres, driving auroras, and in some cases, stripping worlds bare. Earth, fortunately, is not defenseless. Deep beneath our feet, molten iron churns in the outer core, creating electric currents that generate a magnetic field. This magnetic field extends far into space, forming what scientists call the magnetosphere. Imagine Earth as a rock in a river. The solar wind is the current, rushing around us. The magnetosphere is the invisible shield that parts the stream, forcing most of the solar wind to flow around rather than through. On the sun-facing side, the magnetosphere is compressed to about 10 Earth radii. On the night side, it stretches into a long magnetic tail that extends hundreds of Earth radii into space. Inside this protective bubble, life has flourished. For the International Space Station, this shield is everything. At just 400 kilometers above Earth's surface, the ISS orbits well inside the magnetosphere. It does not sit in empty, unprotected space. Instead, it rides within a magnetic cocoon that deflects most of the solar wind before it can reach the station. Without this shield, conditions would be catastrophic. The solar wind would erode our atmosphere over millions of years, just as it did on Mars. On shorter timescales, satellites and astronauts would be bathed in lethal doses of radiation. The magnetosphere is the unsung hero of our survival, and the silent protector of every spacecraft in low Earth orbit. Here on Earth's surface, we are protected by two layers of defense. The first is the magnetosphere, deflecting most of the solar wind. The second is our atmosphere, which absorbs the high-energy particles that manage to slip through. But the ISS doesn't have an atmosphere above it. So what keeps it in orbit without being blown away? The key is understanding scale. The solar wind is made of particles, tiny protons and electrons. They carry energy, but they have almost no mass. Their pressure on spacecraft is minuscule compared to Earth's gravity. While the solar wind can influence the tails of comets or nudge very small satellites over long timescales, it cannot knock something as massive as the ISS out of orbit. Gravity rules here. Earth's pull is far stronger than the feeble push of solar radiation. The ISS is locked in orbit not because of atmosphere, but because it is constantly falling around Earth, its forward speed balancing the pull of gravity. So in orbit, the station relies on the magnetosphere, not the atmosphere, for its main defense. The magnetic bubble deflects the charged particles, keeping conditions far less hostile than they would otherwise be. Yet protection is not perfect. Some solar particles do slip inside the magnetosphere, especially near the polar regions where field lines converge. These intrusions create the dazzling auroras, curtains of light that dance across northern and southern skies. But they also mean extra radiation for spacecraft. In 1958, during the very first American satellite mission Explorer 1, scientists discovered regions of trapped radiation circling Earth. These became known as the Van Allen radiation belts. They are zones where charged particles spiral along magnetic field lines, bouncing back and forth, forming intense belts of radiation thousands of kilometers above Earth. Fortunately, the ISS orbits below most of these belts. Astronauts aboard the station avoid the highest concentrations of radiation. Even so, they still receive doses about 10 times higher than what we get on the ground. Over 6 months in orbit, an astronaut is exposed to roughly the same radiation as 1,000 chest X-rays. This is why NASA closely monitors solar activity and why astronauts cannot live in orbit indefinitely. The exposure is manageable, but not harmless, and it underscores the importance of Earth's magnetosphere. Without it, those doses would be far higher, and life in low Earth orbit would be unsustainable. While the magnetosphere provides broad protection, spacecraft themselves must do the rest. The ISS modules are built from aluminum and other materials that block some radiation. These walls are thin but carefully engineered to deflect or slow down many incoming particles. Even so, they still receive doses about 10 times higher than what we get on the ground. The ISS was designed not only to house humans, but to house them safely in one of the most dangerous environments ever inhabited. Every so often, the sun unleashes a storm. A coronal mass ejection sends billions of tons of plasma hurtling toward Earth. If one is aimed directly at us, it slams into the magnetosphere, compressing and shaking it like a drum. The results can be spectacular, auroras that spread as far south as the tropics, but they can also be destructive. In 1989, a powerful solar storm induced currents in Earth's power grids, knocking out electricity across Quebec for hours. Satellites can malfunction, radio communications can be disrupted. For the ISS, solar storms mean heightened radiation. When forecasts predict a big event, astronauts shelter in shielded areas, and some station systems may be adjusted to minimize risk. Solar storms remind us that even with our shield, we are not invincible. The sun is a living star, and its moods reach us even here on Earth. The ISS is fortunate to remain inside Earth's magnetic bubble. But what about humanity's future in space? On missions to the Moon, Mars or beyond, astronauts will leave the protection of the magnetosphere. Out there, they will face the full force of the solar wind and an even deadlier threat. Galactic cosmic rays, high-energy particles accelerated by distant supernovae. To survive, we will need new shields. Engineers are experimenting with thick walls of water, which can absorb radiation. Others propose using liquid hydrogen tanks or magnetic fields to mimic Earth's protection. The challenge is enormous, but the ISS has given us the testing ground. By studying how radiation affects astronauts and electronics in low Earth orbit, we are preparing for the day when humanity ventures beyond our planet's shield for good. The International Space Station may orbit above our skies, but it is still under the wing of Earth's protection. The magnetosphere shields it from most of the sun's fury. Its walls and systems provide an added layer of defense, and mission control keeps watch, ready to guide the crew through storms. In the grand scale of the cosmos, the ISS is a fragile outpost, but one cradled inside Earth's invisible shield. It reminds us that life in space is possible not because space is welcoming, but because Earth itself reaches upward, extending its protection even beyond the atmosphere. As we look to the future, we must never forget, the farther we travel from Earth, the more we must carry our shields with us. The sun gives us life, but it also demands respect. And for now, Earth's magnetosphere remains our first and greatest guardian. If you enjoyed this exploration of space science, don't forget to like this video, subscribe to Skyward Space Quest, and join us for more journeys through the cosmos.